Okay. So you can see the screen, right?
Yes, sir.
Okay. So we were supposed to discuss assignment 6, and here is the first question. So it
Sir,
says we need to choose the correct statement. First one is any permutation in Sn can be written uniquely as a product of transpositions. So is it true?
excuse me, sir.
Yes.
So I just have uh some doubts.
Ah,
Um,
so
so so I understand the definition for group actions,
uh-huh.
but I still don't understand the motivation or how to think about it. Can you discuss about it?
Motivation behind group actions.
Yeah, or how to think about it. So that's not clear yet.
So you can in fact so group action is basically you have a you have a set, and a group is acting on it, means it's somehow uh, you can say in some sense permuting the elements of the uh, of that set. Permutation is a bijection. So if the action is uh, uh, like sending each element to a distinct element, means the action is somehow person say faithful, then it's like a permutation. Otherwise, it's just like mapping elements of the set itself to some other element. For example, uh, you have a 2 cross 2 plane. So the set of points you can consider as your subsets, and uh, through rotation or translations, you can send one point of that plane to some other point, right? For example, if you have the map for a fixed uh, point x, you can send it to x plus 2. So the map which maps x to x plus 2, this is like a action on the real line x, because it's but it will be a group action if the acting object is a group and it satisfies certain properties, right? In this case, can it be a group action? So first of all, we need to see what is the acting group. So if we say, okay, the acting group is the real with additions and the object is also the real line, then the action defined by x plus 2, it won't be, is it an action or not? So what I'm saying, so this is just sending x to x plus 2. So, but here the underlying group is missing. So for x defining action, you should have a map like this from G cross object x to x. Now here G is mapping everything to just x plus 2. So the G is not playing any role. So the first property is uh, clearly violated, that it has to be X, so which is not being satisfied. So here, this is not a group action, but it is still uh, some kind of like doing some kind of assignment to the elements of the group of this set X, right? So it's an action, but it's not a group action. Now, what group action does, it somehow systematically reassigns the elements of the set, right? It's a map from G cross X to X. So your X is getting mapped to G dot X. You can think like that. Before the group action, the point was this X, and after the group action, you got G dot X. So this group is somehow shuffling the elements of the set. Now, this shuffling is in a nice way, and that nice way is determined by these two properties. First of all, the action of the identity element, should not disturb the elements. It should be the element should be sent to the to itself, and then the action should respect the properties of should be like inconsistent with the group operation. So GHX is same as uh, G dot H dot X, right? I think this is a definition that you might have seen. So this should respect the. So what does this property means? This property mean, so if you act small h on X and then you act G on X, that is same as if you act the element GH on X. So either you do the composition at the level of group, or you add them individually and do the composition, then the resultant is same. Now, these group actions are useful tools in determining several properties of the group and many geometric objects. Now, your X can be some geometric object, and G is some nice group acting on it. Then, in both ways, you can uh, use this either to determine properties of this G by through the action on some known object, or if you have this G to be known, you can get more about this object using the action. Maybe in the next in upcoming lectures or in some other courses, you might realize that how important is the group's actions in understanding many things in physics and chemistry as well. Basically, you can say whatever you have studied till now is just to have some idea about the group. But if you want to see the practical purposes of it, group action may be considered as the first step. Okay, so maybe whatever I am saying may not make complete sense to you, but as you progresses more on this subject, you will realize that group actions are actually very important in dealing with several other topics, not just in algebra, but apart from algebra in real life applications as well. Okay.
Okay, sir.
For example, the group of rotations. Uh, so as a group, you can study them as just as abstract objects, but why they are called the group of rotations? Because they are actually there is an object for which the rotations are determined using that group. So you have this SO3 group. So it's some uh, uh, what to say, not, yeah, SO3. This is like, you might feel like it's in chemistry, but it is spatial orthogonal group. So it's a subset of your matrices, 3 cross 3 matrices over reals. Now, what this group does, it is actually the group of rotations uh, of some particular type for your R cube plane, not just plane, for your uh, three-dimensional coordinate system. So it's a group of special orthogonal matrices. It has some matrices of this type, I think, and it's here you have this 2 cross 2 rotation. So with respect to certain axis, what it does? It preserves one of the coordinate and do the rotation in the other two coordinates. Now, this group you can see as a group acting on the set R cube, and the action is through so this A is a matrix, X is a uh, three is a coordinate, say X, Y, Z tuple, and it's a 3 cross 3 matrix. Now you can get the action as simply A X transpose, means you just multiply this 3 cross 3 matrix with this XYZ. Whatever you get is actually the outcome that you would have obtained by sending this XYZ under the rotation determined by this A. So every matrix determines a rotation. And so this action is just sending this element to a to the resultant uh, that you will obtain uh, through the rotation determined by this matrix. So many such things can be understood in terms of group actions, and there are also proofs of some important group theoretic results through group actions. So as a statement, you won't feel like it may be proved using group actions, but uh, if you look at the proof, then it heavily relies on the group action properties. Like I hope you might have seen the orbits and stabilizers and orbit stabilizer theorem for group actions, or no?
Yes, sir. I have seen the orbits and stabilizers.
So there is also an orbit stabilizer theorem, right?
Yes, sir.
Yes, so that theorem is very crucial in proving some very good theorems in group theory, and thus it makes group actions a very useful tool. Okay, and for the moment you can just see it like that. You have an object X, and there is something which is going to make some shuffling in the elements of X, and so for example, this is your capital X, and uh, there are some elements in it. So what G is doing, G is acting on it, means G is just doing some shuffling and making the elements X uh, uh, G1, X1, and G2, X2, and so on, right? So it's like uh, shuffling of these elements into some other, which again lie into this set. So that's what the map says. You have X, you have some G, and the resultant is just G dot X, which again inside X. Like your vector space, on vector space you have some transformations, right? What transformations does, they are from V to V, sending the element small v to T of V. You can also see this as a group action. Group action is just you take set of all invertible transformations and act it on the vector space, and the action is just S- T of V, T comma V is T acting on V. So this is also a group action. So basically, you have a group and which is just kind of doing some rearrangements in the elements of the set X. And that rearrangements are not happening in an arbitrary way. As I said, you can send small x to x plus 2, the example that I gave, but it's not a group action. So group actions means rearrangements in a very nice manner, and that nice manner, that those two properties are really crucial because you want to obtain some results uh, for group actions, and for obtaining those results you need some basic properties to be there, and those two properties just signifies, first one is the action of the trivial element should be trivial, that it should not disturb the set capital X. Second is there should be compatibility with the group operation. Okay, I hope I may be like over defining things, but it just to give you some idea. Okay.
Okay, sir.
Okay. Did you get something, or like, or did I confuse you more?
No, sir. Think it's fine.
Okay. So now let's proceed with the assignment problems. Any permutation in Sn can be written uniquely as a product of transpositions. So is it true?
Yes, sir.
Is it? This is true. Okay. What's the explanation?
So uh, consider some permutation A1, A2, A3 up to AK, where K is less than or equal to N. So,
Permutation or a cycle?
oh, cycle.
Okay.
So now we'll uh, consider the transpositions such that so I consider only the two cycles A1, A2, uh, A2, A3, and so on. And
So this A1, A2. I hope you have checked the calculation. Okay. This is A1, AK, right? That's what you mean to say? Or it's other way. Here A1 is mapping to AK. We should get A1 mapping to A2.
so the other way, I think.
Right here A1 is mapping to AK. So is it like that? A1 mapping to A2, A2 is not there, so that's fine. A2 mapping to A1, here A1 would be mapping to A3, so A2 would be mapping to A3. Similarly, like AK1 is mapping to A1, A1 is mapping to AK, so AK1 will be mapping to AK, and AK is not here, there, and here it will be AK mapping to A1. So this is okay, uh, but the word uniquely, can you write it as in a unique way? For example, you have say uh, in S4, consider sigma equal to 1, 2, right? So uh, it's already a transposition, right? Then sigma is 1, 2. It is also, we can write it as 1, 2, 3, 4, 3, 4. Isn't it? So there are distinct ways of writing sigma as a product of transpositions. So, am I audible?
Yes, sir.
So the word uniquely is there. If you remove it, then it's okay. Any permutation in Sn can be written as a product of transpositions. And the proof is basically you write every cycle as a product of transposition. Now every permutation is a product of disjoint cycles. So you just keep on writing the cycles as transpositions and that will do. But here the word is uniquely is there. So which creates the problem. Okay.
Okay, sir.
So you miss that and tick the wrong option, right?
And somehow it turned out to be right, but I didn't think about the uniqueness.
Now, if in this example also there are two options correct, then you would have done some more mistake, right?
Yes, sir.
So this is not correct. And now let sigma belongs to Sn. Suppose sigma is this, then sigma I and tau j are two cycles for ij. Then 2 divides k minus r. How to do that? So we have some hint, although I think this problem was also discussed in lecture notes, right? Now, how to proceed further? So you are given that sigma I and tau j are two cycles, right? So you can write this thing as sigma 1 to sigma k, then tau 1 to uh, tau r whole inverse is equal to identity, right? And this will be sigma 1 to sigma k, tau r inverse, tau 1 inverse equal to identity. Now, since identity is an even permutation, and tau I inverse are also two cycles for all I. Therefore, you cannot write identity as a product of uh, something, a product of odd number of transpositions. So this means that K plus R is even. And the reasoning is even permutations cannot be written as a product of odd number of transpositions. Okay. So now K plus R is even. This implies K plus R minus 2R, that is K minus R, is even. Right? So the second part is correct. You made a mistake here, or is it correct?
I made a mistake, sir, but now I realized.
Okay. Now, third one, K cycle can be written as a product of K minus 1 transpositions. Here, it's not claiming that the uniquely part. So whatever you said earlier was correct. So let sigma to be A1, A2, AK belongs to Sn, be a K cycle, then sigma is equal to AK, A1 AK, A1 AK minus 1, and A1 A2, right? So it is true. This implies sigma can be written as a product of K minus 1, 2 cycles or transpositions. Okay, fine. What about the next part? This is not correct. Why?
Well, since 3 is correct.
Since
Oh,
this
so the parity would be opposite, so it can't happen.
was right. So since each K cycle can be written as a product of K minus 1 transpositions, writing uh, and else can be said, nothing like that is since each K cycle is can be written as a product of K minus transpositions and uh, simply therefore a K cycle cannot be written as a product of K transpositions, and the reason is what you did, what you just gave. The parity is cannot be changed. means product of K transpositions has different parity when different parity from the product of K minus 1 transpositions. Let me just rewrite it in some more understandable language. K transpositions and product of K minus is a product of K transpositions and a product of K minus 1 transpositions has have different parities, right? But it can be written as a product of K my K my to say uh, K plus 1 transpositions, right?
Um, so, but um, even for K plus one, uh, there would be the same problem, right?
No, you have already written a K cycle as K minus 1 transpositions. Now I'm saying, can I write the same cycle as a product of K plus 1 transpositions?
Oh, yes.
K
So,
minus 1 and K plus 1 have same parity, right?
yes, yes.
And how you can do that?
Just put the same two cycle twice.
Again, right? Very good. So you need at least K minus 1 transpositions, and you can actually do with any transpositions of the number of transpositions of the form K minus 1 plus 2R, right? Where R is some uh, uh, either a natural number or zero. Okay. Okay. So this completes the first question. Let me just uh, take the second question. Still, let SN denote the symmetry group on n letters. You already know this notation. Choose all the correct statements. The set of two cycles in Sn generates Sn.
Um, yes, sir.
Reason?
So, well, any permutation can be written as uh, product of transpositions. So,
Great. So any permutation can be written as a product of transpositions. Okay. The set of even permutations in Sn generates Sn. Is it true?
The second statement is not true.
Reason?
So the even permutations generate only the even permutations. So the odd permutations will be left.
I couldn't get even permutations.
Will generate only even permutations.
Will generate only even permutations. Good. So I can write like since a odd permutation or any odd permutation cannot be or more precisely the set of even permutations generates the even permutations in Sn generates the subgroup An, and An is strictly inside Sn. So, uh, well, we can just say instead of generates, forms the subgroup, right? The set of even permutations in Sn, because uh, everything is inside An, and any element of An is again an even permutation. So the set itself uh, subgroup. So the set of even permutations in Sn forms the subgroup An, and An is strictly contained in Sn. Therefore, uh, that's it, right? That's good enough, I guess. So it cannot generate Sn, right? Because it's already a subgroup which is properly contained in Sn. So if it's a group, then what will be the group generated by a group? That's the group itself. Okay. By generation means the smallest uh, group containing those elements. But if it's already a group, then that's itself the smallest one, right? So it cannot take anything from outside. Okay. The set of odd permutations in Sn generates Sn.
This is true.
Reason.
So this set already contains all the transpositions.
So the same thing I can write here, and all transpositions are odd permutations, right? What about the last one? Three cycles. Same reasoning will come. The set of three cycles in Sn. Here it will be like generating not the subgroup. Generates is An, and An is properly contained in Sn. Okay, I hope that is clear. Here comes the question on group actions. So, uh, if you have solved this example, you can see that in each step, some action is happening. The element small s is from the set itself, and n is coming from the group. So, n star s is n plus s. So, you can think like s is being mapped to n plus s using n. So, there is some rearrangement of elements is happening in all the four cases. So you can say in all the four cases there is some action, but the question is whether those actions are group actions, whether those actions satisfies those two properties of group actions. Okay. Mm.
Okay.
Now the first example, G G with a group of integers under addition, and S with a set of real numbers. Now, what this set of integers is doing, it is just sending the small element small r, small s to n plus s, right? In one of the example that I discussed this, we were just mapping x to x plus 2. So you can see here, it's this in 2 is replaced by x plus g, right? There we are having map from uh, g cross x to x, right? So g is your n and x is your s. So that was also an action. It was just scaling some uh, point, right? But that is not a group action because that doesn't comes into the nice framework that we have designed to create it as a tool to study some other properties. Okay. So the first one, is it a group action?
Yes, sir.
Okay. So the first property is uh, we should have 0 star s to be s again, right? Is 0 plus s equal to s for all. I should write small s for all s in capital S, right? And what is the second one? Second one is n m star s. That is, this is with respect to the group operation. So here, group operation is addition n plus m star s, which is n plus m plus s, right? And that is same as n acting on m plus s, and that is n acting on m star s. And that is also happening for all n m belongs to G and for all s belongs to capital S, right? Just give me a minute. Just a second. Right. Okay.
Sir, the screen's now. Oh, it wasn't visible for some time, but it's
Ah,
visible.
so I was just checking whether the rule is this or it is written in some other manner. So I'm just looking at the lecture note. So this M star N S is, the same convention is there. I'm just putting N first and then M. Okay, so it's in alignment with the lecture notes. That's fine. Okay, so it forms a group, uh, group action. Now, what about the second part?
This is not a group action.
This is
Not a group action.
why?
So, um, so consider 0 times s.
Like
That will always give 0 instead of s. So the first property is violated.
some equation. So 0 time s is 0 s, which is 0, not equal to s. Therefore, it is not a group action. Also leave it. This can be 0 when s is 0, right? But we want it for all, right? So thus it violates the first property and it is not a group action. Instead of since I should write therefore. Okay. So this is a group action, but this is not. What about the third one?
This is not a group action either. Again,
Same,
the same reasoning can be
same
used.
reason, right? So the third is same as second. What about the fourth?
This is a group action.
This is a group action. R star is a group of non-zero real numbers under multiplication. So here, and R star S is RS. Did I use some? Oh, that's right. So first one is that S belongs to S. Then 1 star S is 1S, which is S, or on, even this is okay. And B is, let R1, R2 belongs to G, and S belongs to S. Then R1, R2 of S is R1, R2 times S, which is R1 times R2S. That means R1 star R2S, and which is same as R1 star R2 star of S. Okay. Now this is in for any arbitrary R1, R2, and for any S, therefore this satisfies the second property, and star is a group action. right? I should not write it is. There is nothing like it is here. So you should also be careful with your words while giving an answer, right? It somehow changes the entire meaning. Okay, let me just take the third question now. Oh, sorry, it was the third one. So let me take the fourth one. Hmm. Let G be a finite group. Consider the action of G on itself by left multiplication. In other words, if GA belongs to G, then the action of G on A is defined as G star A to be just GA. Choose all the correct statements. First one is given AB inside G, there always exists an element G star, there always exists an element small g such that G star A is B. So, in other words, first option says that there is only a single orbit for this action. So pick any element, you will get another element such that through this action, you can map that element to the element you started with. So there is a single orbit. All elements are interconnected. So is it true?
Yes, sir.
Oh, that is also an option. I didn't realize. The first and uh, third are same, right?
Yes, sir.
It's just like rewriting uh, it in a different way. And if you prove this, that there is exactly one orbit for any group, then second and fourth will also be uh, discarded, right? Because this is for any group G. So a million case groups are also covered and symmetric group of in three letters is also covered. So if for any group you are proving that there is exactly one orbit, so there cannot be two orbits for some groups, right? Okay. So how to prove the first one?
Pick G such that G equals B A inverse.
Okay, so given D belongs to G, there exists uh, G equal to uh, given AB belongs to G, they are given A and B both we need to find. Given AB belongs to G, there exists uh, G equal to B A inverse, right? Belongs to capital G such that G of star of A, which is its multiplication, right? So B A inverse A, which is just B of, we are using the associativity property, and then that is just B identity, and which is going to be B. So the first one is correct, and similarly, third one is correct, but second and fourth are not correct. Okay. It's, it's very easy question, I guess. You just need to solve one part, and the other three parts are uh, by default solved. Now we have almost a similar question. with but the group action is changed. Instead of the multiplication group action, now you have the conjugation. Can we say the same things here, or will there be a change?
They will be different.
There will be a difference. What is the difference?
So the first statement is not true here.
First is not true. Reason.
So if I take A to be the identity, then uh, then the whole orbit will just be the identity.
Oh,
So I um, can't find some G such that G times A equals B.
okay. So orbit of identity is a uh, singleton set, right? You're absolutely correct. Take A to be the identity of the group, then G star A is just G star identity of the group, which is G, EG, and G inverse. That is again EG, and that is happening for all G belongs to G. This implies orbit of EG is just um, singleton set EG. So this is, or if it is understood, then I won't write. So it's by EG, I just mean the identity of the group, right? What about the second and third option? Again, if you solve one of them, then you are done with the other also. So for a cyclic group of order 10, how many orbits should be there? Exactly 10 or 1, or maybe both are wrong, then something else.
The second statement is true.
Second statement is true. Huh?
So since it's cyclic, I know that it's abelian.
Hmm.
So G inverse is G times G inverse times A,
Good.
which is just A. So for every element I take, the orbit will contain only that specific element. So I'll have 10 distinct orbits.
So, so we can even take all the three options in one go if you prove this claim. So if G is a group, and small g belongs to the center of G, then the orbit of G with respect to the conjugation action, or even I can remove this part. If G is a group, then the orbit of G with respect to the conjugation action is a singleton set G if and only if G belongs to the center of G. Do you agree? So first understand the statement. So if G is a group, then the orbit of G with respect to the conjugation action means the collection of all element of the form uh, here. G is a acting element. So I should write uh, A with respect to the conjugation action is a singleton set. Of course, we need to assume that if G is a group and small a is inside G, then the orbit of this action is orbit of A with respect to that action met actually makes sense. So it's a singleton set if and only if singleton A, if and only if this A is coming from center of G. So do you agree with that?
Yes, sir.
And the proof is exactly what you said, right? So in first case, let A belongs to center of G, then orbit of A is what? This is just the set G A G inverse for all G belongs to uh, G, right? This set, this is what? This is G inverse A, and that is singleton A, right? Now, if second part is if orbit of that's first part, second part is I should not write uh, these enumerations. Maybe I will just write it as in some star point. This is also a notation for action. What to do? Write 1, 2. So let A belongs to G be such that orbit of A is singleton A. Then for any uh, G belongs to G, G star of A will be GA G inverse, and that is A again, and that implies GA is equal to AG, right? So, and this implies A belongs to center of G. Listen, if and only if statement, right? Clear?
Yes, sir.
Okay. Now, all the other parts can be proved using this. In part second and third, if G is G is a cyclic group, let us first prove it without going into the parts. This has one corollary, which says if G is abelian. Then the number of orbits of G with respect to the conjugation action is equal to the order of G. Now let us first prove this corollary, or let's write it as an if and only if statement. So the number of I don't want to write it again. Orbits of G with respect to the conjugation action is equal to the order of G if and only if G is abelian, right? And it comes directly from this claim. You know how? Let's let's start the forward direction. If let the number of orbits of G with respect again, I don't want to write this again, with respect, and I need to write with respect to the conjugation action is equal to the order of G. Let's assume that. Then for any G belongs to G, orbit of G has to be a singleton element, right? If we are using small a, then we can go with that also. Now for any A belongs to J, uh, orbit of this A should be a singleton element, right? Because if for any element it, it is more than one element, then the orbits forms a partition of G, right? Of orbits of two elements are same only if they lie in the same uh, orbit, right? So either the orbits are distinct or they are equal. So if orbit of A is some uh, is not a singleton set, say it is more than one, then for all elements which are inside that orbit, their orbit will be the same and that has size more than one. So the number of orbits will exceed the order of G, right? And Okay. So, and definitely there is at least one element in the orbit, because if you take G to be identity, then A is mapping to A itself for any action. That was the first rule of group actions. The first rule says that A is always inside the orbit. So the, the number of orbits has to be less than equal to the order of G. But if it is equal, then each orbit has to be singleton set, that is itself the element. Okay. And which implies A belongs to ZG, and this implies ZG equal to G because A was an arbitrary element, and thus G is abelian. Clear?
Yes, sir.
And second part also, just uh, reverse the process. G is abelian implies ZG equal to G implies A belongs to ZG for all A belongs to G, and that means orbit of A is singleton set, and which that is also for all A belongs to G, and which implies order of G is equal to, let me just write like that, size of the collection of all orbits of A, uh, such that A belongs to G. Right? This size of this set, number of orbits, is same as order of G. So this proves the claim, right? The corollary. Now we can move to the question itself. And instead of cyclic, even if we have abelian, then that is also fine. And fourth one is G is not an abelian group, then there is an orbit of order at least 2, which this also comes from this corollary itself. Because if it is not abelian, then the number of orbits is not equal to the this is number of orbits of G with respect to uh, okay, I just moved it. I should have copy pasted it. So, right, you got the point? So,
Yes, sir.
okay. So we have just obtained a more generalized statement. Second is correct, third is not, and fourth one is also not correct. Oh, fourth one is correct, right? We have non-abelian if they register uh, orbit of size order at least 2. Okay, so let me move to the final question, I think, of this assignment. Okay. Let S6 denote the symmetric group on 6 letters. Let A denote the number of transpositions in S6, and B denote the number of even permutations in S6. Choose all the correct statements. So number of transpositions in S6, how many are there?
A is 15 and B is 360.
Why?
So for the uh, For considering all possible transposition, there are two places and six symbols. So
Hmm.
I first consider all possible permutations on two places,
Hmm.
and for any cycle AB, it's same as BA. So there's uh, so I divide the number of permutations by 2. So I get 6 times 5 by 2, which is
Okay.
15.
Or we can say that you are just choosing two from six, right? Combination. So it's 6C2, right? Just give me a second. So yes, so there are two ways to see. First, you can just see like there is two cycle. So first place you have six options. Second place you have five options, and AB is same as BA. So 6 into 5 should be divided by 2 for this repetition to account for this repetition, and thus there are 15 options. Another way to see is this is same as choosing 2 from 6. So you know permutation and combination. So this is same as 6C2 because in combinations also we don't pick uh, choosing means we consider some ordering. That means if we have chosen A first and B the second, then we won't be considering the option B and choosing first and A again, right? So in any way you can see this. So let me just go with whatever you suggested. So let sigma sorry equal to AB belongs to S6 be a two cycle, two cycle or transposition. It's be a transposition. Then mm, there are six ways to choose A, and if A is chosen, then there are five ways to choose B. Also, the selection, or I should make also the permutation instead of the selection. Also, the permutation AB is same as BA. Thus, the total number of transpositions in S6 are 6 into 5 by 2. That means 15. Good. Okay. What about the second one? Number of even permutations in S6. Why it is it 180 or 360?
360.
Why?
So this is A6,
Uh,
which has 6 factorial by 2 permutations, which is
so how
6.
you know that the cardinality of AN is half the cardinality of SN? So we need to prove that, right?
Yes, sir.
You have some idea in which we can do? One
Um,
claim is for any n, size of AN is size of Sn by 2, that is n factorial by 2. It's simply a counting problem, right? You have a set of permutations, and now you have a set of even permutations, and uh, it's a counting problem. But can we use some kind of group theoretic concept to solve this counting problem? Now here comes our homomorphisms in picture. So consider this map. Consider the map from Sn. Sorry, and let me denote it by a sign. Will it be a good notation? No. Let me just go with 5. Uh, from Sn to Z2 or Z mod to Z. But sigma is mapping to which, what should be the map? So, first that phi of sigma is 0 if sigma is an even permutation and phi of sigma is 1 bar if sigma is an odd permutation. Now, can you tell me whether this map is a homomorphism or not?
Yes, sir. This is a homomorphism.
Why?
So phi of sigma 1 times sigma 2.
P of identity is 0, right? That is first thing one can easily check because it's a even permutation. And now, what about uh, the composition thing?
So we need to check if phi of sigma 1 times sigma 2 is equal to phi of sigma 1 times phi of sigma 2.
Right. So there will be many cases. First case is the sigma 1 and sigma 2 are both even or both odd permutations. Then what will be both odd permutations? Then what will happen? Then sigma 1, sigma 2 is an even permutation, right? If both are of the same parity, then after multiplication, you will get even permutation, right? Which implies P of sigma 1 and sigma 2. This is 0 bar because you have uh, even, this is even, so you have this to be 0 bar. And this is same as P of sigma 1, phi of sigma 2, which is also 0 bar. Because if they are both odd, then this will be both 1 bar. 1 bar plus 1 bar is same as, so I should not write like product. I should write with the notation addition modulo 2, right? That's the operation here. So if both are odd, then this will be 1 bar and 1 bar, it will be 0. If both are even, again this will be 0, right? And so now what if they have this different parity? If sigma 1 and sigma 2 are of different parity, no matter they are even or odd, then definitely sigma 1 and sigma 2 is an odd permutation. So this will implies phi of sigma 1, sigma 2, which is 1 bar, is same as phi of sigma 1 addition modulo phi of sigma 2, because this is again going to be 1 bar because one of them is 0 and the other one is 1 bar. In both the cases, you have uh, phi of sigma 1, sigma 2 is same as phi of sigma 1 and sigma 2. So it covers all the cases. This implies phi is an homomorphism. Now, how to use this fact as a uh, how to use this to obtain the cardinality of an? That is also one thing, right? We have proved that it's a homomorphism, but we started with the problem that we want to determine the size of n. Now, with respect to this homomorphism, what is the significance of n? Can you write an as something related to this homomorphism?
Mm, well, it's a normal subgroup.
For normal subgroup, you don't need this phi at all, right?
Mm.
See the definition of this phi and tell me uh, what an what role an plays here, and means, can you say an is something with respect to this homomorphism? So if we restrict this phi to an, what will you obtain?
Oh, then I'll get only zero for all sigma.
All sigma. So then what is An? And is it zero for anything outside An?
No.
So An is precisely the kernel, right?
Yes.
Right? This implies phi is an homomorphism. Also, by the definition of phi, uh, kernel of phi is same as An, right? And what is the image of phi?
Set two. Oh, I think I see the proof now.
Now you can see.
Yes, sir.
So can you
So,
help me to complete?
yeah, the first isomorphism theorem can be used here.
So by the first theorem of isomorphism, Sn by the factor group, right? Sn by An is isomorphic to Z mod 2Z. And in terms of cardinality, what will we get? This implies size of Sn by An, which is same as size of Sn by size of An is same as size of Z mod 2Z. And this is 2. And hence, size of Sn by 2 is same as size of An. And this implies size of An is nothing but n factorial by 2. Right? So whenever you are asked to give the size of a normal subgroup and you know the size of the group, always try to construct a homomorphism. Now, with respect to each normal subgroup, there is a natural group homomorphism for which that normal subgroup is a kernel. So, given any n normal in G, one can define the map from G to G mod n, and the map is just send small g to the first factor Gn. What is the kernel? If this is phi, then the kernel is n, right? So every normal subgroup is realized as as a kernel of some homomorphism, and for every homomorphism, kernel is a normal subgroup, right? Now the idea is how to see this G mod n as a some known group. So here uh, G mod n is just Z mod 2Z. So we started with taking Z mod as n as Z mod 2Z and then proved that actually uh, it comes like that. Okay. So if you are given any normal subgroup of a group and one is asking about the cardinality, then you start with some intuition uh, that what should be the nature of G mod n, and then once you know the group G mod n, Define a homomorphism phi from G to that known group in such a way such that the kernel comes as the normal subgroup for which you are intended to find the cardinality. So it's a very common trick in group theory to estimate the size of the normal subgroups by defining a suitable homomorphism. Okay. Okay. So now you know that in case of 6, n factorial is 720, and then thus this 360 comes as that correct option and 180 is wrong. Okay. I think that finished the assignment. We still have some time, so maybe we can discuss some practice problems. Are there some good practice problem questions? First one is okay. Okay. There are not good problems from here. Let me just see what was there in the last year's assignment. There also the same kind of problems are there. So maybe we can. Okay, let me just see if there are 2, 3 options in the practice assignment which can be discussed. So this is from the practice assignment part. First question, which of the following are group actions? For first one, what is your guess?
No, sir.
Why?
Um, so the identity times is should give me S, but here it always gives me 1.
Correct. So uh, 1 uh, simply E star S is not equal to S if S belongs to 2, 3, or 4. Right? So this is not a group action. What about the second one?
This is a group action.
So this we have already done, right?
Yes, yeah.
Third one,
Again, not a group action. So identity times S should give S, but here it's not necessarily true.
so identity times S is not S if S is not identity, right? Okay. So this is not correct. This is also not correct. What about the fourth one?
This is a group action.
This is a group action. Why?
Um, so if I consider the identity matrix uh, times V, then I always get V. So the first property holds.
And
And
okay. And
so if there are two matrices A1 and A2,
hmm,
the associativity also holds. A1 times A2V is same as A1 A2 times V. So the even the second property holds.
okay. So this is for also. What about the last? They have already been done, right?
Yes.
Under addition, this is not true, but this is okay. Now, second part has some interesting thing. Let me just paste it. Hmm. So G is acting on the set S. One has to choose the correct statements. Let S belongs to S. G such that the set is a subgroup of G. So is it true? This set contains all elements in the group, which fixes the element small s.
Yes, sir. I think this is true. So,
Why?
so for the given set to be a subgroup, the
Mhm.
identity element should belong here. And
Right,
since, um, sorry, sir.
right. Go
Okay.
on, please.
So, since this is a group action, I know that the identity element belongs to the set.
Right.
And suppose some element G belongs to this set,
Hmm.
then since the identity element also belongs to this set, it can be written as G inverse times G. So, and since this is,
Hmm.
yes, since this is associative, I can write this as G inverse times G times S, which gives G inverse times S. So G inverse also belongs to this set. So this is a subgroup.
Okay. So first of all, we should check, or we should always check the closure. That's the first property. Okay. So is it closed?
Yes, sir.
So let GS belongs to. Oh, it's a subgroup. So for subgroup, checking that closure identity and inverse, that is good enough. Associativity always holds, right?
Yes.
Because it's a subset already. So uh, then mm, GH star of S is same as G star H star S, right? But H fixes H fixes this S, so this will be S, and then G again fixes this S, so this will be S, which implies GH belongs to the stabilizer. So I'm saying the word stabilizer because this subgroup is known as the stabilizer. The word itself signifies that it stabilizes the element small s, right? So this subgroup has a particular name. Now the second property we should check is, as you pointed out, the identity, right? Since uh, identity star identity of G I should write is same as S, therefore identity of G also belongs to this stabilizer set. Now, what about the third one? Let G belongs to stabilizer of S. Then as you pointed out, we can use the uh, compatibility of the group action, group operation. So 1 dot s is this is or I should write like that. Then s is same as 1 star s, which is same as g inverse g star of s, right? But due to the property of group action, now you might be having feeling that why we choose those two properties, right? If we don't have those two properties, then the concept like stabilizers won't be existing, and you won't be having the stabilizer orbit theorem because stabilizer doesn't make sense then. Stabilizer won't be a group, right? The first property ensures that identity is there in the stabilizer, and the second property ensures the closure, also the inverse. So it gives a nice shape to the stabilizer. Okay. So now this is same as G inverse star G star S, right? But what is G star S? This is again uh, S. So G star is also stabilizing S. This implies G star S is equal to S because S is there. And that implies G inverse belongs to stabilizer of S, and thus stabilizer of S forms a subgroup of G, right? What about the, uh, let us go to the next part. S1, S2 are two distinct elements in S. Then we need to check whether this set G belongs to G. G star of S1 equal to S2 is a subgroup of G. Is it a subgroup?
No, sir. The identity does not belong to
Very
the.
good. So, uh, since identity does not belongs to, let's say this is some set H, therefore H is not a subgroup of G. What about the other properties? We can't say anything, right? Because once G mapped S1 to S2 and H is also mapping S1 to S2, we can't say whether G, G star H will map S1 to S2 because once it is mapped to S2, we don't know, right? Okay. Let S1, S2 be arbitrary elements. There always exist an element G in capital G such that G star of S1 is same as S2.
Again, this is not necessarily true. So, in the assignment, um, it was seen that when we take conjugation,
Good.
this
Counter
statement
example.
doesn't hold true.
So counter example, take conjugation action on a non-abelian or just an abelian group will work, right? Not just on an abelian group. and abelian group G, which is not the trivial group, of course, and S1 not equal to S2. I have solved the entire question in the here only. That's fine. Right. Now, what about the next part? Fourth one. So you
Fourth one.
understand this, right? If you have the abelian group, then the elements are distinct, means the orbits are distinct, right? So S1, S2 won't be in the same orbit. Okay.
Okay, sir.
What about the fourth one?
Fourth one is true.
Fourth one is true. Why?
Mm. So G1 times S1 is 2.
Hmm.
So G2 times S2 can be written as G2 times G1 times S1,
Good.
which is G2 times G1 times S1. So if I consider uh, G3 equals G2 times G1, then I get uh, G3 times S1 to be S3.
Good. So precisely right. Okay. Maybe we can discuss one more problem, or if you have any doubt, then we can discuss.
No doubts, sir.
Okay. The other practice problems are same, means of the same nature. I can just like reshare my entire screen and tell you. uh, So you can see this screen, right?
Yes, sir.
So the other practice problem are of the same nature. So this says we have the multiplication action on the left on the group. Well, the action is the left multiplication, and then given two elements AB, there is always exist an element such that G star A is B. So this we have already seen, and now we have already this implies that there exists exactly one orbit. So this third option discards, and second is just a special case of first. So I don't know why they give the same question in the practice assignment and assignment, right? It's exactly same. This fourth one is different, right? So here they are asking about the size of the stabilizer. For any element A, the set G belongs to G, uh, where G star A is equal to A contains exactly one element. So is the size of the stabilizer same? Is one for every element?
I think this is true, sir.
Okay.
Only the identity.
Only the identity will be there because uh, only identity stabilizes this. Now, you can also see this through orbit stabilizer theorem. Since the orbit is entire group, so stabilizer should be singleton element, right? So this is true, right? For any element A, the size of the stabilizer is 1. It contains exactly one element, that is precisely the identity. Okay. Now, there exists a group G and an element A belongs to G such that this contains at least two elements. Again, it's just a negation of this. So we are done with that. Now, if we consider the conjugation action, it's asking the same thing. For all AB, does there exist G such that G star A is P. So is it true? This will be true if and only if A and B are in the same conjugacy class, right? Now, do all elements in S3 forms a single conjugacy class? No. If you take just A to be identity, then this won't be true. If uh, if you just take, you have three choices for conjugacy classes: identity, or any two cycle, or any three cycle. So if you just pick A and B from different conjugacy classes, this statement won't be true. Second one we have already done in detail. Now there is a group of order 4 which admits exactly one orbit. Is it true? Hello?
No, sir.
Reason?
So again, this was seen in the assignment. There are at least two orbits in this case.
So what is special about the group of order 4? Yeah, you are also saying correct that there are exist. So identities always just contain the identities. So orbit of identity is singleton set. So there will be at least two, but group of order 4 are abelian. So here exactly four orbits will be there. So you can also see like that. That's why they have stated those groups which are abelian. Group of order 4 and group of order 13. Both are abelian. So the size of the group will be same as the number of orbits. There is an last one is there is always an orbit containing exactly one orbit that is for identity. And for G to be S3, there are exactly two orbits. Is it true? For S3, there are exactly two orbits. No, right? First one is for identity, second is for two cycles, and third one is for three cycles. You can check that these three are the orbits for the conjugation action. So there will be three orbits, not two. Okay. Okay then. So now I think we can stop here. We will be meeting on the next Tuesday at the same time, and that would be our last class. So you can come up with any doubt in the assignment problems till assignment 7. I think assignment 8 has deadline beyond that, right?
Yes, sir.
Let me just check the deadline for assignment 8. Uh, it is it is 17th September. So we won't be able to solve assignment 8. So that would be an exercise for you. You can solve, you try to solve that of your own, and till assignment 7 we will be discussing. If you have any problem in assignment 8, you can write to me through my mail ID. Okay.
Okay, sir. Sir, can you share your mail ID?
Okay, I will share once I stop the recording. That would be fine, right?
Okay, sir.
Okay, so let me end the session, and we will meet on next Tuesday at the same time. Okay.